Okay, okay, okay. So again, so I was saying I'm talking about Mascar CNN, which is a network that is useful for doing both instance and semantic segmentation. So instance segmentation is kind of like I guess you would say like the holy grail of computer vision in the sense that you're doing both object detection and then you're also applying a mask to those detected objects, classifying them. So you can kind of say which pixels belong to the classified objects, which versus which ones don't. And that's kind of useful for in a TEM context because you can get some quantitative data about the image, such as the number density of defects, the size of them, how many bubbles you might have, and what size their average size and stuff like that is, which can be useful for predicting properties. Um, so, so to give some background, I'm going to kind of explain building up from CNN to RCNN to faster RCNN, and then finally to mask RCNN, because these kind of add consecutive improvements in terms of capabilities. So as we've kind of like covered like in some detail, the basic form is the convolutional neural network. And when we talk about convolution, we're talking about multiplying each region of the original image by kind of like by a matrix of values or weights, and we call that like the kernel. And you kind of raster that across an image. And the idea is that each time you multiply a region of the image by the kernel, you're extracting like small features of the image, like its edges, like that. And you do that several times over. You extract larger features from those smaller features, and usually you can kind of downpool in a sense that like you might like make some generalizations about the data that you've extracted until you can finally do something like a classification. And then you can, yeah, like it says, downpooling, like one of the things you can do is like a max pooling operation where you just have the matrix values, you pick the highest one in there, and that becomes the new single entry value for a smaller matrix that represents the information in the image. So standard CNNs like this are really great for classifying like a whole image. You say like, oh, this is an image of cat, dog, person, whatever. When it comes to object detection, though, that's kind of like a higher level in terms of what's required, because now you're not just classifying one whole image. You have to do an arbitrary number of classifications within one image. You have to determine how many objects there are, like where they are, their specific locations, stuff like that. So in order to do this, you kind of have to subdivide your image into several regions. Okay, here's person one, person two, whatever. The kind of brute force way to do that would be to subdivide the entire image into many, many small images, and then try to like classify each of those individually. But that becomes, obviously very computationally expensive. You're running each small subsection through a CNN over and over again. And so, that can also be difficult if you're like trying to look at objects of different sizes as well. So what RCNN did, which just stands for region-based convolutional neural network, and as I said, Mascar CNN is eventually based on this, is it applied an algorithm called a selective search algorithm to kind of automatically identify what are the regions of interest within an image. And so I'll kind of switch back and forth between this slide and this one. And so what that does is it kind of looks at different pixels, like it kind of starts with an arbitrary number of proposed regions, no more than 2,000 differently shaped regions to kind of put a limit on the processing time. And it kind of looks for similarities between each region and its adjacent region. If they're similar enough, it'll group them to one region and then kind of go through that several iteratively, recursively adding more and more regions until you kind of have like, okay, these are the main regions of interest. And this the type of algorithm replied, I don't really know the specifics of this, but they call it a greedy non-maximum suppression algorithm, which is, it's reliable, it gets the job done, but it's pretty slow, especially compared to what we have now with faster and mask RTN, which we'll get to in a bit. But yeah, so in any case, once you have these final regions of interest, you kind of work them down. So because they're going to be like, as you can see here, you have like a lot of rectangular shaped regions, just like the, especially like that cloth in the background of the horse is not really a perfect scale, neither is the guy riding it. And so you kind of warp it down to like that square image you can see right there in the middle. And that's what you pass to the convolutional neural network layer, and that will classify it. And you can see that once you identify the region of interest, it kind of draws like this little bounding box around it to say, okay, this is the position of the object you're looking at. And then, so after you kind of do this classification, you run it through CNN. Usually use a pre-trained network. So one of the most famous ones is BTD16, which is a network that's been trained on a lot of general image data. That's not really specific to any particular application, has like thousands of different objects and stuff like that. So that you kind of limiting how much you actually have to train the network from scratch before you get a good fit. So yeah, that's generally what you run it through. That's the kind of CNN you do after that. And then at the final step, you apply a bounding box regressor algorithm, and that just adjusts the position of the bounding box so it like more accurately fits the position of the object after you have it classified. So this is kind of the ground level for region-based convolutional neural networks. As I said, the problem is that's slow, so people kind of made this effort to improve the speed by developing faster RCN. And the real step that this took is instead of applying the selective search algorithm on the base image, with it instead is you run it first through a convolutional neural network, just kind of like the early layers of the convolutional neural network, and that extracts some features. So you do some down steps, you're reducing the amount of data you're searching through, and that allows you to kind of streamline the process for doing a selective search algorithm. Those improved the speed a little bit. The rest of the network is pretty much the same idea. Slight differences, for whatever reason, this one they applied a soft maximum classifier, which means you give like the probability of an object being classified as what you've given it, rather than just saying like, oh, it is a person or a horse or whatever. The problem with this is that it's still not fast enough for large data. So that's why they decided to move on to faster RCNN. And this was the real like the kind of game changer, because basically what they did is they recognized that the selective search algorithm they're using was way too slow, and they replaced it with another neural network. They developed this called a region proposal network, which is specifically trained to find the regions of interest in a more efficient manner. And that's the rest of the network after that is kind of the same. Once you have to identify this region, it's just the same. You pass it through a neural network, you classify it, you adjust the bounding box position. So this was this started to get people fast enough to actually being able to handle large data. And once they had this done efficiently enough, people started to think about, okay, how do we move from this finally to instant segmentation? So the goal was to advance from these simple bounding boxes they had, just saying this is the position of the image, to saying, okay, let's classify each individual pixel in the image. Does it belong to the object we've just detected, or does it belong to the background or to a second object that may even have the same classification? So this is what we call instant segmentation. And it's kind of superior information you would get from just semantic segmentation, which is something you might do with an algorithm like UNet, where you have several different objects. Like you might have like 20 people in an image, but it would just say like, okay, this is where the people are outlined their shape, but it won't distinguish one person from another. So that's just semantic segmentation. This is kind of one step above that, because you're doing object detection first. And so what's really kind of groundbreaking, the kind of like key piece of technology that Mask RCNN innovated, was developing this algorithm called ROI align. ROI just stands for region of interest. So that kind of deals with this problem, which I'll explain kind of verbally, which is that when you identify regions of interest through like this this region proposal network, you have like these regions, they're kind of arbitrarily positioned. They may not really line up with points on the feature map they've done. So I can skip back and forth here and there. You can see like this little, I don't know if I have like a pointer, but you can see like the faint blue lines in the background. That's kind of like your feature map. Like that's like a matrix of values. And this is like, and that like orange box is the arbitrarily defined region you have on top of it, and it doesn't really line up. So if you were just to kind of, I think I have a note here. Yeah, you have like an arbitrary kind of length that you scan by whenever you're doing like a pooling operation called the stride length. So it's like if you're moving 2 pixels at a time across the image, and you're saying, okay, I'm gonna like take this, like make this little block, this 2x3 block at this position, pull all the values into one value, then move it by 2 pixels to the right, pull all the values of that, and that's how you're building like a smaller matrix. The problem with that is that if the size of your region, which has been arbitrarily defined, is not perfectly divisible by the stride length, you're going to have some leftover room on the edges. The way the algorithm works is that if it's just rounding those numbers off, because it'll crash if you round it, you're losing information at the edge of the region. So you're going to have less accuracy that way. And so what they kind of did here to solve that is they developed this algorithm that they'll kind of, whatever the size of your output matrix you want to be, once you like pull to the values, you define kind of 4 points within each of those bins. And that's those little blue dots there. And then you kind of do a bilinear interpolation from the 4 nearest points on the feature map underneath that. And that kind of gives you an average value, and those values are weighted based on how close they are in the feature map underneath. So you're getting information from all of the edges kind of surrounding the region, as well as the whole interior of the region. So this is really important for improving the accuracy of like the classification once you actually have an arbitrary region defined and also the masking. And then finally, the feature that mask-R-CNN has that allows it to do its masking operation is it uses something called a fully convolutional neural network as like kind of like the head of it. And so the real challenge when you're doing a mask operation like this is you don't want to lose too much information when you're downpooling. Because you think about it, you might downpool to you're losing data each time you like kind of like condense these values. And that's useful for classifying, but then once you come back to having to apply a mask, you have to kind of do up steps as well. And it's like, okay, does this pixel belong to the classification I just defined or not? And you're losing a lot of information is going to have a very coarse kind of resolution, if you will, if you're just doing that straight away from like the fully pooled matrix. So what you do is you have these little skip connections with these little dotted arrows at the bottom. So say that like that pool 5, which is kind of like a blank box, I mean, this is like a very condensed or very highly pooled matrix. You add to it some information from pool 4, that's what the little sum symbol is, and that gives you a slightly higher resolution mask, essentially. You can do the same. You can add pool 3 to that further, and you're getting more and more information. So that's why you apply a fully convolutional neural network. That's what this architecture is described as for a masking operation. And yeah, that should give you a fine enough resolution to kind of apply a mask to the image. And this is usually run kind of in a parallel step to the classification and also the bounding box progression. Mask-R-CNN, even though you're kind of doing the more advanced version of applying mask to the image, they also still do give you the option of applying a bounding box to the image to give a position for whatever use you may want. And then I would say just one more thing about mask-R-CNN as a good feature is that because it's a meta algorithm, it has kind of these different modules associated with it. So you have like, you have this FCNN as the head, you have the region proposal network, you even have like the convolutional network at the bottom. If any one of those single like networks is improved in some way or it's better trained for a specific data set, you can just kind of plug them in and out and it still works together and improve the whole network as a whole. Like you're not going to have major interference if you like change one of those components. So that's kind of an advantage for why I think it's still being used after a few years for this kind of image detection. And then, of course, there's still room for improvement just on the basic function of mask-R-CNN. There's still cases where object detection fails or the segmentation may fail. So you can see in the bottom left image, it's kind of pointing at like 2 people that were failed to even be recognized in the object detection or even like classified versus on the right, you can see that like the mask of that one person that's like color like yellow has overlapped with another person that hasn't been fully detected. But again, this is a selected example of a failure. Overall, it's doing pretty good. You can see that you have a lot of different people that are all overlapping each other, and it's able to tell which person is which, able to apply them, even if the one person is really large in the foreground versus that really small purple person in the background. It's also able to classify each of them as people versus there's a small image on the left that's high versus someone's cell phone in their hand on the right. So like overall, it's doing pretty amazing. But like again, this is a selected example of how it's failing. And this is a pretty egregious example on the right of where it actually failed a classification, which I think is more rare, where it classified a little beach blanket as a kite. So there's always still room for improvement. But I think these 2 images I got were actually taken from when mask-R-CNN was a little more fresh, which was like 5 years ago. So hopefully there have been some improvements since then. I imagine I wasn't able to find any more recent results, but I imagine that there have been some improvements. Okay, so now I'm going to move on to talking about how this was implemented in a paper that I found. I was actually surprised I was able to find a paper that's specifically on radiation-induced defects using mask.
Yeah, only one, and this is from Robert. Yeah.
Yeah. So that was kind of a pleasant surprise, I guess. I don't know, I wasn't expecting that. Yeah, I think this just came out this year, 2022. I'm pretty sure, if I remember correctly. And yeah, so in this case, they said that they were applying semantic segmentation in a sense, but to me, it kind of seemed more like an instance segmentation in the sense that they were collecting size data of each of like the individual dislocations and things that they were measuring. But either way, that's like semantics. So they also mentioned in their paper that in previous work, people had used UNet to perform segmentation, but they were unable to distinguish between different defect types in the same image. So this is kind of like an advancement to say like, okay, let's classify several different defect types and get some data about them based on this network. So in this specific work, they were looking at classifying three types of defects, either 111 dislocation loops, 100 dislocation loops, or these black dot defects, that's what they call them. I think it's just smaller interstitial clusters that haven't fully formed into like a loop form, but they appear as tiny black spots or dots on the TM micrograph. So as would be expected, especially for TM data, they use a transfer learning approach for this, with models that have first been trained on the widely available ImageNet and Microsoft COCO data sets. This is especially important when you're training on TEM data, where the amount of images you have is inherently limited because not everyone has a TEM that they're taking photos with, especially because it's you often have to focus on a specific material, a specific set of imaging conditions. So in this case, they're only updating the terminal layers of the network. The early layers of the network are not being trained; they're kind of frozen in place. And in this case, what they're looking at is their defects are being classified based on STEM bright field images, specifically of Fecal alloys of limited composition range that are taken along the 100 zone axis. The reason it has to be along the 10 zone axis is that they're kind of classifying the dislocation types based on the shape. If it's elliptical, it's a 111 dislocation. If it's a 100, it'll be either circular or kind of like a line shape with a edge on. So first what they try to do is the model attempts to first recognize instances of each defect versus the background. Again, that's that region proposal network kind of coming into play. And then applies that through the CNN kind of layer. And that kind of classifies it either as a 100 loop, 111 loop, or a black dot, kind of based just on its shape and size. And then after that, it applies this mask head to determine kind of the size and shape of each defect by classifying each pixel in the image as either background, 100 loop, 111 loop, or black dot. And that allows you to kind of finally extract some material data from the images, such as what the defect density and size distribution and stuff like that are. So these are some of the images that they've kind of cross-compared. So on the left of each of these three blocks, you have the manually labeled kind of like ground truth that they were training it on, and then like right how like kind of performed. You can see overall, like I mean, at a glance, they look pretty similar. If you look a little bit closer, you can see. I don't really have, you can't see my mouse, can you? No. Let's see. I feel like it's easier to point these things out. Is it like on the little green drop down? No.
Yeah, you're fine.
Okay. Well, oops. I don't see it, but I'll try to like barely describe. I don't know, like for instance, like in the bottom left of like the right set of images, the ground truth, like you see, there's like a tiny blue dot. It's like the most left blue dot compared to the right. It's it's red, so it's supposed to be a black spot. It classified it instead as a I believe that's a 111 dislocation loop. Yeah. So it's like I think especially to have like the size kind of as a determining factor for whether it's one of those loops or if it's a black dot. I think there's some more egregious areas in here as well. That might be kind of hard to point out without a pointer. But overall, you can see that like at least like on the grander scale, it looks like pretty good. And I also have some more statistical results here showing how well it did at predicting them. So on the left graph, you can see kind of how well it did at predicting the number of each of these defects versus the size of those defects. And you can see that like it's slightly under predicted the small 111 loops. That probably makes sense because it's probably confusing them with the black dot features versus the larger ones. It's kind of under predicting them, and it's kind of a similar story with the 100 loops as well. But overall, you can see the data is pretty correlated pretty well, especially with the like the defect sizes. That's surprisingly well, and that's like the masking portion, which is kind of I would kind of consider the more impressive portion, the masking. I see that kind of like where it's weakest is in determining the circularity of these 100 type loops. That's arguably might be a bit of a less important feature, at least if we care about properties of the material anyway. But I mean, I guess being able to determine whether or not it's circular ellipticals also kind of plays into misidentification of the 111 loop versus the 100 loops in classification instances. Yeah, and then you have like some large outliers here, like it's like all the way on the right of that true defect densities per image. The black dot is way off. So, but other than that, it seems to be doing a fairly decent job of predicting these. So I would say it's definitely a successful implementation of MaskR CNN for this kind of data. But of course, the limitations is that mostly that it's very specific. You're only looking at frequency alloys of a limited composition and processing range, and you can only look at it under bright field STEM images along the 100 zone axis. And then furthermore, you're only looking at these kind of low temperature radiation defects in the BCC alloys. So you have two different dislocation loop types and interstitial clusters. So ideally, if we're going to apply this kind of model to other TEM images, you'd want to include other kind of simultaneous defect types and be able to differentiate between them all, including cavities, including bubbles, voids, Stacked-Bell tetrahedra, other dislocations like type of loops. Especially if you have like an FCC material, you're gonna have a whole different set of Burgers vectors possible. You may not even be able to classify them based on shape alone. And if you have precipitous as well, that's another one. And one thing I was thinking about, because like we just talked about G.B analysis a lot in classes, I was thinking like might be cool if you're able to have sets of images that are grouped together, if they're taking the same region of the sample, different orientations, different G vectors, and tell the algorithm, hey, can you identify where the loops are in these images, track their position, because you should have a bounding block box applied to each, see when they disappear, and then from that just kind of like automate the G.B analysis, and that should be allow you to get like kind of speed up the process of finding what the Burgers vectors are, especially in a more complicated material that might have all kinds of different Burgers vector dislocation loops. And then, of course, as always, there's always room for improvement in the accuracy of defect size, distribution, and the density. So, yep, that's about all I got. Questions?
It was nice. I liked the examples of the paper that you provided. That was very much related to what we would be doing. Yeah, and you're right that the application is limited. For like there they have done on STEM images 100 zone axis. They had very easy defects that they were literally identifying. So if I give you, as you told that you would like to do a G.B analysis on more FCC on every Burger vector you want to just see. So as you see that it's a very complicated paper it would be if we are able to develop such thing. But as an initial step, if tomorrow I give you a research project and I ask you to apply Mascar CNN, and you have read about it, its limitation, now, that we need bigger data, what kind of data, do we need? So what kind of experiment would you do irradiation wise and on what type of sample so that you can apply this model?
Are you talking about specifically trying to extend this model to other types of materials and defect types?
Yeah, I mean, just propose me a research experiment where you can easily apply this model.
Well, I think probably the easiest one would be if you're just to increase the radiation temperature and look at like bubbles and voids, those type of defects, because those you can classify on shape alone. If you're kind of going for the harder idea I was thinking about and actually trying to automate G.B analysis, probably you'd want to do is look at maybe an FCC material where you can have more different types of defects present. I'm not entirely familiar in the background yet of different radiation defect types, but I imagine there's different conditions you can apply that you can have, both imperfect loops and perfect loops in the same material. I don't really know the kinetics of how that formation or radiation condition. I imagine playing with dose rate as well, or not dose rate, but total dose as well would be relevant. Yeah.
So in this paper, they presented a comparison with the UNet, and you mentioned that Mascar CNN is superior than UNet in many ways. So what is so it is superior in what way? I know that UNet does semantic segmentation, Mascar and RCNN does instant segmentation. Apart from that, why do you think it's more superior?
I think that's kind of like the key feature in the sense that you're not just getting defect density, which you could get from UNet, but you're also getting like size information, size distribution, that kind of stuff. And I think that could be, it's just kind of giving you more quantitative information than you would get from just semantically segmented image, you know. In terms of like efficiencies and stuff like that, I didn't research UNet too much. I just thought this was a comparison that, like, in terms of what it's capable of doing in terms of segmentation, is a bit of a higher level.
Because I was just thinking, when you do semantic segmentation for easier projects, like if you have to do cavity and voids, where you don't care, this is cavity 1, this is cavity 2, this is cavity 3, all of them are cavities. Maybe going through a simpler model is a first good step. When we do these kind of experiments. Other than that, I have a question on the architecture. If we can go to the architecture slide for Maskar CNN.
Sure. Any particular one like this?
So here, it was very interesting. You pointed out that from FastRCNN to FastRCNN, main thing is that in your FastRCNN, you had your selective search algorithm. So in selective search algorithm, so you give your algorithm an image, and then it starts performing selective search algorithm, on it. That means it is able to extract features, or it is able to extract different regions that it proposes. So for example, if an image contains, car, cat, dog, it is able to propose that this region is interesting based on, because it has a similar color, because it has a similar kind of texture, or it has something like that. In RPN, do you have an idea what, so in selective search, they use it based on either size, color, texture. That is the way that, the initial regions are proposed. But in region proposal network, what are they using?
That was kind of like the next question I was kind of curious to answer myself. I didn't really get a chance to explore it too much. But I mean, I imagine they have a set of training data that are going to say like, oh, these are the regions of interest as well. And they just kind of, train it to the point that it's able to say like, look at, I guess, I mean, being a neural network, it's probably extracting features from it, just saying like, oh, this is a homogeneous color region. This is, a circular type of region that might be like bounding some kind of shape or something like that, and then kind of use that to predict whether or not it belongs to the same object or not. I'm just kind of talking off the cuff there. I don't really know for sure. I didn't really get to do that much.
Okay. Yeah, because this is kind of an important information. When you select your data, so it's very helpful, because in FastRCNN and in RCNN, you have the data where you have a bigger objects where you can literally point out cars and these things based on the bigger sizes. But think about the smaller objects. In our case, we have little voids, little black dots that you saw in Maskar CNN. And just that knowing the right algorithm, what it is picking, it just helps you to choose the correct model, especially for those kind of features. Like, on what basis is it proposing that this is an object?
Yeah, and I think it has like proven in terms of like some of like the general data that like it's good at picking up objects that are the same classification, very different sizes. Like you can see the two purple people in this images are very different sizes, but it's still able to kind of classify them both despite that. I imagine that's kind of what's generalizing to its pretty decent performance in the implementation for the radiation defects.
Yeah.
But yeah, it would be nice to know specifically what's kind of going on beneath the surface. But I imagine it's just kind of doing the same thing that other neural networks do, which is extracting features locally and then kind of using that. I guess it's just the classification at the end steps and the later layers are a bit different. You're not really classifying the image. You're kind of saying, oh, this belongs to a distinct region.
So. Right. Okay. Another quick question I have is on the slide where you were explaining uppooling. You were explaining upsampling, right? And yeah. So here it's very interesting because you got two things going on. One is your feature map. That is simply a feature map that we discuss in the class. When you give it a cat, and it takes a feature map in terms of numbers. and then compress the information in terms of lower or a simpler number by applying pooling. So all of the information is compressed into few numbers. So it's like, you're losing the resolution that in a very simple language. So here in MaskR CNN and also in other version of RCNN, I think faster, where ROI pooling plus your so ROI pooling plus your feature detection are overlapped, right? Where you were explaining me that kind of extrapolation, I think, it is trying to just apply that kind of algorithm. And if you're when you use a kind of what do you call that thing? Slide the window, and if the size is not
the stride length.
Yeah, the stride length is not equal to your ROI. In that case, you lose the information, right? So what is the remedy to it?
To losing the information in the leftover stride length?
Yeah.
I mean, that was kind of what the point of this ROI outline algorithm was. Yeah. And because in here, it doesn't perfectly overlap with the feature map. But if you say you have a point at the corner, in that top left corner, even though the two corners at the top are outside of the region of interest, it's still getting information from that because it's part of the bilinear interpretation. So it's going to be weighted less because it's further outside the region, but it's still getting some information from that.
So this is the state-of-art algorithm that MaskR CNN employ, bilinear interpolation, that it's trying to kind of simply interpolate the information here. And because it knows the stride is smaller and you cannot do anything about it because it depends on the size,
Yeah.
And so this is the state-of-art algorithm that we have that is just interpolating the points that we have missed. Maybe there could be something that you call as padding. Have you heard about padding?
Kind of adding some extra length that the stride go over. Yeah. I think the problem, I'm not sure, I haven't really looked into that much, but I imagine the problem is you're still going to run into an error if it's it's rounded off in the sense that the size of the regions you're looking at is arbitrary, right? So I guess you could have some over, but then you might also be extracting too much information from something outside of the region. So then you kind of have to play with the padding and kind of finely tune it, I guess, to we're getting accurate enough. Whereas I feel like this is a little bit more stable, at least in the idea, is the sense that you're always going to get less information from just outside the region of interest and more information from just inside the region of interest. But you're still going to be getting information from those edges,
Right. So yeah, I think it makes sense. So that's why they apply this simple algorithm and they just try to extrapolate, because sometimes I think even such kind of interpolation we also loses because ROI we are getting only the center of the cat, but rest it's trying to just extrapolate everything.
Yeah, I think that was the thing. At least when I saw people present, I was watching some videos of people presenting MaskR CNN kind of for the first time 5 years ago, and they were really proud of this feature. I think this is kind of what they're saying, oh, this is the thing that makes ours a little more accurate than anything beforehand,
Yeah. So in MaskR CNN as an output, are you getting the bounding box as well?
Yes,
or you're just getting the masks?
Yeah, you're getting both. I think I said that at some point. Let's see here. Yeah, well, in any case, yeah, you're having both. You're having three things. You're having the classification, the mask, and the bounding box. I mean, the bounding box is depending on what you're looking at, may be kind of obsolete or gratuitous if you already have the mask, but it might be useful in some instances. I guess even when I was talking about if you're doing, automated G.B analysis, you kind of want the exact position or the relative position of each dislocation comparing across images. So I guess it could be useful in the context like that, to have that bounding box, especially if it shifts slightly from.
Yeah, because in generally, have you heard about little bit about YOLO? The presentations, there were many presentations that happened in past 2 weeks about YOLO. So there they are using an algorithm. Okay. When you have the masking, there is semantic versus instance segmentation is happening. That means each pixel is you're classifying pixel wise. What I'm trying to say here, and other thing in YOLO is that you train the object when you start training the data. So if I give you the void data, so you literally, provide a bounding box around the void as a training data. Now in Mascar CNN, are we doing the same thing? We are just giving the data as the bounding box, and also there is a masking. What is the input data?
I didn't read too much about this in detail, but at least based on what I can hear,
there's a ground truth.
Yeah, like they're providing a bounding box, but there also looks like they're delineating the inside of each effect. I imagine that's probably not done by hand, or it might be. But I imagine there's probably simple algorithms you could apply to just find the edges of something once you have a bounding box. You can have a microscopist look at this image and just, draw a box around it, and then, through edge detection like that, say like, okay, this is the mask of this dislocation loop. Once you have that step done, that might be speed up the annotation process. That's kind of what I imagined they were doing. It's possible it's done by hand, but that seems kind of overly tedious.
Right. Yeah, because my thing is like here you have to provide the bounding box plus the mask, and then you are getting that kind of information.
Mm-hmm.
Yeah. So here, what is the advantage of giving the bounding box?
In terms of the annotation or in terms of the output?
Yeah, in terms of anything. Like we are already, by the color itself, we know the size.
Yeah, I think I don't know about in terms of like annotating it. Maybe that's just because that's what Mascara CNN requires for training, especially since it's outputting a bounding box. But I think probably what the designers of Mascara CNN have in mind is probably you're already applying the mask. You kind of already calculated the position when you did the region proposals. Why not include the bounding box?
Yeah, because it's a little bit puzzling for me because in your algorithm, I just did not find there should be a separate branch leading to a bounding box regressor.
Yeah, I didn't get an image of that, but it is like you basically have three parallel things at once. You have the classification, you have the mask generation, and then parallel to that also is the bounding box regressor.
Okay.
Yeah.
I think this bounding box regressor, is it an optional thing or is it there?
I'm not entirely sure. That would have been useful if I had time to actually like
apply it.
This, but I didn't because other semester end of the semester.
Yeah, I mean, you will have time. This is just to provide you a good foundation to start thinking. The idea was to.
Yeah, I imagine you should be able to turn off. I mean, at least in terms of the output. I don't know if it would save you.
Yeah, because honestly, I don't see. Looking at the results here, what extra information does it provide? Like.
Yeah.
To me, it looks like a redundant.
Yeah. And that's like kind of what I was saying earlier. Like if you were to automate a G.B analysis, I think that it might be useful in the sense that a bounding box gives you kind of a more general position of a defect, whereas like a mask is very precise. So if you have like an image that's slightly shifted because it's taken under a different G orientation like that, if the mask is kind of off, it might throw off its ability to track one dislocation to another or something like that. That'd be a guess for me or something. I don't know. Other applications where you might want a bounding box.
Yeah. And like in these images, they did not care about those dislocations which are at the back, right? Like they cared about the loops, but they never cared about the dislocations,
Yeah, not the line dislocations. Yeah. So. Yeah, I guess that was interesting as well. I wonder if maybe because like they just assume those line dislocations are kind of there from cold working at the steel or whatever, just naturally, and they only cared about the radiation induced ones. Hardening, not the ground mechanical properties or the base mechanical properties.
And do you think with machine learning you would be able to separate those lines? It looks tricky, right? Maybe semantic. Yeah.
I imagine you might have some difficulty with the ones that are overlapping, but I mean, this has already kind of been impressive in the sense of its ability to detect overlapping objects, but maybe not such like thin line-shaped ones like that, So I'd wonder if that would require like a slight modification of the algorithm or something like that. I don't know.
Yeah. Okay, I think you were very clear about this paper, which is good. Yep, I think that's it.
Okay. Thank you.
Right. Okay, I'll sign off. Bye-bye.
Bye. Happy holidays.